Now in this video we'll see the Fourier's law and its applications in heat transfer. Now this video we have recorded on Samsung Galaxy Tab with S Pen. Hope you will enjoy this writing and this explanation and the video. So let us start with the video and the explanation. First application of Fourier's law is to the infinite slab. Now we know that the governing equation in this particular case is heat flux Q upon A is equal to minus K multiplied by temperature gradient dt by dx. Cross multiply by dx. So on the right hand side we will have minus K multiplied by dt. So we have cross multiply by this particular term. So Q upon A integration, the limits of x are from 0 to b. So integration of dx is equal to minus k. The limits for dt are from t1 to t2. So at x is equal to 0, t is equal to t1, and at x is equal to b, t is equal to t2. Now integration of dx is x. So this is q upon a. Integration of dx is x. The limits are from 0 to b is equal to minus k. Integration of dt is t. The limits are from t1 to t2. In place of x, we have to substitute the upper limit, that is b, minus the lower limit, that is 0, is equal to minus k as it is. In place of t, upper limit is t2 minus lower limit is t1. So it is q multiplied by b divided by a will be equal to minus sign. If you take inside, it will be t1 minus t2. Now b upon a term we can transfer on the other side as a upon b, keeping the other terms as it is, that is k t1 minus t2 as it is. Now rearrange the term in such a way that in the denominator we'll have b upon ka. So above equation can be written as t1 minus t2 divided by b upon ka. And this particular term is known as what? It is the thermal resistance according to the electrical analogy. And the units for this thermal resistance are: width B is in meter, thermal conductivity K is in watt per meter Kelvin, and area is in meter square. So meter as it is, meter Kelvin will get transformed. Meter Kelvin will get transferred from denominator to the numerator, and watt meter square will remain as it is. So this meter Kelvin which we have written over here is transformed from denominator of the denominator, it will go in the numerator. Meter into meter, that is meter square, that will get cancelled out. So unit of thermal resistance is Kelvin per watt. Now the another application of Fourier's law is to the infinitely long hollow cylinder. Here area is perimeter into length. Perimeter is 2 pi r multiplied by length, and then cross multiply by this dr on this side. Now here the variable is r, that is the radial direction, that is the radius, instead of x. So we can say that q upon 2 pi l as it is, dr upon r will be equal to minus k dt. So variables are now separated. The limits for r are r1 to r2, and temperature is from T1 to T2. So Q divided by 2 pi L. Integration of 1 upon R is log R to the base E. The limits are from R1 to R2. Integration of dt is T, and the limits are from T1 to T2. Now in place of R we have to substitute the upper limit, that is R2. So it is log R2 to the base E minus log, in place of R substitute the lower limit, that is R1, minus K. In place of T it is T2 minus T1. Upper limit is T2 minus lower limit is T1. Now log M minus log N is log of M upon N. So it is log of R2 divided by R1, or ln of R2 by R1 to the base E, minus K. take minus sign inside. So instead of T2 minus T1, it will be T1 minus T2. Now cross multiply by this term, that is 2 pi L over here. So it is 2 pi Lk T1 minus T2 divided by this term, that is log of R2 by R1. So here also, by keeping the temperature difference in the numerator, we can derive the expression for the thermal resistance. So this above equation can be written as T1 minus T2 divided by ln of R2 upon R1 divided by 2 pi Lk. So this term which is present in the denominator is known as the thermal resistance. And what are the units for this thermal resistance, that also we will see. R2 upon R1, as it is a ratio, it is not having any unit. 2 pi is also not having any unit. So it is L length is in meter and K is in watt per meter Kelvin. So we can cancel out meter from the numerator as well as from the denominator, and this Kelvin will go in the numerator. So it is, the unit is Kelvin per watt. So again we know that thermal resistance is having the unit of Kelvin per watt. Now for hollow sphere, we'll see the application of Fourier's law to the hollow sphere. The governing equation is same, that is Q upon A, that is the heat flux, is equal to minus K. Here also we have to take into consideration temperature gradient as dt upon dr, where r is the radius and r denotes the radial direction. Cross multiply by dr, so it is minus K into dt on the right hand side. Now surface area for the sphere is 4 pi r square multiplied by dr is equal to minus K multiplied by dt. So therefore Q upon 4 pi term will separate the variables, will arrange dr upon r square. So r square is arranged in the denominator and rest of the terms are as it is. The limits are from r1 to r2 for the radius, and for temperature it is T1 to T2. Integration of 1 upon r square is nothing but integration of r raised to minus 2, and then we have to use the formula of x raised to n, that is x raised to n plus 1 upon n plus 1. So that will give you r raised to minus 2 plus 1 divided by minus 2 plus 1, that is minus 1 upon r. So we can say that this is nothing but q upon 4 pi minus 1 upon r. Just now we have seen the limits are from r1 to r2. Right hand side minus k, in place of integration of dt is t. The limits are from t1 to t2. Now take minus sign outside first, and then we'll see how to apply the limits in this particular case. Now substitute the upper limit. So it is 1 upon r2 minus 1 upon r1. Take minus sign inside. So k into t1 minus t2 as it is. Now cross multiply by this r1 to 1 minus r2 into 1 divided by r2 r1. So r1 minus r2 divided by r2 r1 is equal to right hand side as it is, that is k into t1 minus t2. Now take minus sign inside, so that instead of r1 minus r2 we'll have r2 minus r1 in the numerator, and rest of the terms are as it is. Now we'll cross multiply by this term over here. So it is 4 pi k r1 r2 t1 minus t2, just rearranging the terms, divided by r2 minus r1. So again, keeping the temperature difference in the numerator, we can say that r2 minus r1 divided by 4 pi k r1 r2. This entire term which is present in the denominator is the thermal resistance as per the electrical analogy. And let us see what are the units for this. So again, radius is in meter. So we can say that the numerator is having the unit of meter. 4 pi is a constant. K unit is watt per meter Kelvin. R1 is in meter. R2 is also in meter. So meter, and this meter, and meter in the numerator, that will get cancelled out. This K will go in the numerator, so it is Kelvin per watt. So these are the units of thermal resistance in case of the hollow sphere.